his in his experience, he has published more than 30 plus Scopus Index paper that includes IEEE transaction, Elsevier journals, etc. The past 5 years, he has collaboration for his publication with the University of Romarty, Italy, NTU Singapore, Regline University Australia, University of Sutton Scotland, Albang University Denmark, etc. He has established his research contact across the global, which includes Japan, South Korea, Australia, Scotland, Denmark, and Italy. Further, he was one of the key persons to establish a solar research cell for the School of Electrical Engineering at Velu during his MTech tenure. In addition, he is a recipient of prestigious fellowship offered by South Korea under Korean Research Fellowship. Prasatram is currently associated with Pohang University, South Korea, as a postdoctoral researcher. So, on total, he has 7 years of research and teaching experience. So, in this delightful occasion, I welcome you, sir, to take over this session.
Thank you so much, sir. Am I audible to everyone, sir? If there
It's
is
audible.
any,
It's audible. It's no issues.
yes, sir,
Perfect.
if there is any kind of audio noise or something like that, just stop me, and wherever if there is any problem, I'll be happy to address it.
Yeah, sure, sure. We will inform. No issues.
Yes, sir.
Okay.
Thank you so much, sir. So, very good afternoon, participants. Probably it's good evening for me, and it's good afternoon, maybe late evening, I can say. So, thank you so much for the invitation, Utrasamy sir, JK ma'am, and I owe my respects to HOD of the department, Dr. Vicky sir, and my fellow colleagues earlier in the Department of Electrical Engineering, KPR Institute of Engineering and Technology. And I hereby take a moment to introduce a topic for a PV system. It is order of the day, where we call it as reconfigurable PV systems. Huge amount of research potential is possible in this reconfigurable PV systems, where maybe every 10 days once we get a publications, we get a good amount of research attention towards this reconfigurable PV systems. And how this reconfigurable PV systems is going to be an inevitable tool for a battery storage system is going to be the topic. So how can we as an electrical engineers have some input to this PV system, so that it has some bottlenecks or problems in PV. So how the power can be enhanced? As you all know that PV is itself cursed by some kind of efficiency issues, but still PV has now become order of the day. I have so many proofs out of it. At the end of the session, the participants of the session might be knowing how to design a PV system with battery for their particular home, or for their particular shop, or for a small nano grid kind of a system can be designed at the end of the session. That's a guarantee I can give you. And I have shown one problem where how a PV, for example, if it is going to be a 2x2 system or a 3x2 system, how the PV system can be configured for accordingly to a battery can be utilized intelligently. So this is the outcome of the session. Probably at the end of the session, you all might be knowing, and in between, I'll be informing how this research area can be a value added research area, how this research area can be published into can be taken into a research area and worked on it. So these are all the overall agenda of the topic: design of reconfigurable PV systems for efficient battery storage. So straight away, I'll get into the market opportunities first. So don't have a data because the 2020 data is not available with International Renewable Energy Agency. Why? Because 2020, we all know that it is a very big pandemic period. So the data are very tough to collect during this period, because many of the installations has been stopped. So I just stick on to the data of 2019. So when we see the data of 2019, as you know, in solar photovoltaic stands at the top, where the employment opportunities in renewable energy, in out of all hydropower, wind energy, and all those things, solar photovoltaic, the generation of opportunities were something like 3,754. In on almost it is in all the technologies, the solar photovoltaic is going to be the pioneer. So we can easily label that 3,754,000 jobs are created in solar photovoltaic system. I recently know a few of my friends have taken over the job in Bangalore city for empowering micro nano grid installed PV systems. So that is the amount of market rate that we have in terms of renewable scope. So definitely, maybe in future we might have a stream, maybe a machine learning based solar photovoltaic energy systems, or in the future we might have a particular narrowed down engineering course with respect to solar photovoltaics. Who might wonder? That is the scope of solar photovoltaic. So, and the next one is going to be the amount of investments where it is being made in the year between 2005 2019. You can see a steady rise in exponential rise in solar photovoltaic installations, particularly in the year 2014 to 2019. If we can clearly see a steady investment of 2 to 250 billion USD billion to 300 USD billion is constantly invested. That shows the amount of interest towards a global market that stands for renewable energy, particularly solar energy. We can see that all the yellow contributed to only to solar energy, which means that the potential in solar energy, the potential to electrify the entire world via green economical ecosystem based power resources is of high interest. Maybe it can be a good marketing opportunity, maybe it can be a good business opportunity for many of the entrepreneurs. Many people are coming out with market business with respect to solar energy, with respect to power converters, with respect to installation of PV systems, with respect to battery management system. Many areas are opening it out. Many research areas are coming out with respect to solar PV systems, and particularly young budding engineers, young researchers have been the eye openers for many of the technologies to come out. So this is the market rate over the investment made in solar PV. So, and particularly maybe this slide is quite maybe invisible. Sorry, probably if people would see in a good clear skin, maybe they might be knowing. This particular slide speaks about India, where India is standing. Maybe 1 by 10. There we have seen. There we could have seen 100 billion, 120 billion has been invested. Whereas here we can see every year India is consistently, particularly in 2018, India is investing 10 USD billion, which means 1 by 10th of the world share is shared by India. So, and this is very important slide. Why this slide is very important, I'll say. So when you see the countries rate, how that a PV cost has fallen earlier, before 20 years, when we say about photovoltaic, it is just like a television. So before 20 years, when we see about television is just like a taboo, where it is something like a huge thing that is appeared. Similarly, the cost is also very high. It is only for high class. But similarly, solar PV has also been in that rate, where the semiconductor prices and all those things were in the alarming rate, where you can clearly see that 2010 the rate of semiconductor and all those things were very very high. And in the year of 2018, yes, it has fallen down, particularly in the countries like Australia, India, Italy, and all those countries have cut down their PV cost. It is a very important data when we start to write an introduction of a paper with respect to PV. Most of the people will say about with respect to how PV cost has been fallen down, how the economics has improved. It is just purely based on semiconductor. The rate of semiconductor of either maybe silicon or germanium, it has just straight away, it is falling exponentially. It has dropped down. Hence, the market has boomed out. In fact, India is now heading towards building Asia's largest solar power park. That is one of the hugest thing that is going to happen. We already have one set at Gujarat. The another one is in Madurai, particularly in Tamil Nadu. So all those things where the global scenario or the wide aspects of solar PV, where it is constantly being increased in installations. So this is the scope. This is the scope of solar PV throughout the world. This is the scope of renewable energy across the world. So maybe, as I told earlier, in the near future, maybe in 2030 or 2035, definitely there will be a course on electrical engineering, maybe narrowed down based on energy engineering or solar PV engineering or battery management systems. Definitely it is going to be an order of the day. Maybe in the year of 2050 or 2055, there will be no electricity boards, there will be nothing. We might have only a pure based solar PV, independent power grid, nano grids for particular area, where the power from which will be pumped from solar to individual houses, or an individual house is going to be an independent net metering concept is going to come. So these are all the market opportunities where business people or the engineering people are thinking about. So this is the scenario of electrical, I mean solar PV, for being it is completely been empowered. So this is the goal we what the present government is having: empower entire India with pollution free renewable source, and produced 100 gigawatt of power via, this is a older mission, but still is currently is also being installed. As all you know about photovoltaics is nothing but the green source, where it is the modularity and all those things can be small, and the design installation is very simple, and it can quickly react to the peak loads, and it can able to match to the it can able to match to the load demand from the rising from the power system side. And the very important advantage is it does not have any moving parts like induction machine or something like that, generators or something like that. So that is a very big advantage we have with solar PV systems, and provided there is no noise at all, so there is no need of maintenance except PV cleaning. There is huge amount of research papers now coming out with respect to PV cleaning technology. So there is also a huge number of opportunities for PhD thesis to happen in PV cleaning. That is also again a market opportunity for an engineer, for an researcher, where we can think about how this PV cleaning can happen with respect to water technology, with respect to cooling technology. Anything may come up. So this is going to be this is going to be the solution after implementation. So, and it is static, as I have already told you. These are the very big advantages compared to the conventional. So next I'll explain what is an importance of photovoltaic modeling. How an electrical engineer with the perspective of an electrical equivalent circuit can be modeled with respect to photovoltaics. It is just very fundamental. Every device will have its own characteristics. I can say, and every diode will have a characteristics. Maybe I call it as an IV characteristics. Every MOSFET will have an IV characteristics. Maybe it may be a source drain characteristics or transfer current, any characteristics. It may be BJT will have its own characteristics. And when you say it is a characteristics, when we depend it on the characteristics, it tend to operate in that characteristics. For example, if we say a diode has a new voltage of 0.7, when it reaches 0.7, the diode will get turned on, so it starts conducting. So all those things, all its characteristics. Similarly, photovoltaics modeling for an via electrical equivalent circuit, how it is going to be modeled, how we are going to electrically model an IV characteristics by an electrical equivalent circuit, and how it is going to help for the manufacturers, or how it is going to help for the design engineers. That is going to be that is going to be the talk for next 15-20 minutes. So I'll clearly say, yes, of course, we have to model a VI curve of a PV cell, module on array. I'll say what is cell, module and array later. I'll come back to this point. Very important, very interesting point as well. PV cell, module and an array, very important. And how as an electrical engineer, how can we model an electrical equivalent circuit, and how we can define its operating condition. For example, every these things have an operating conditions. For example, if we take an induction motor, the temperature is going to be a huge factor. How it is going to define its character. Similarly, how this equivalent circuit is going to defined by the outermost environmental conditions of a PV. So then and how it is in terms of PV, how it is going to change with respect to irradiation and temperature. All these things has to be put into an electrical equivalent circuit, where we are going to model that electrical equivalent circuit to that is dependent on your irradiation. And definitely it is not going to be an easy task. It is going to be a nightmare task. It is yet again a different research area for people, for budding engineers, for people who are doing research. They can model their own electrical equivalent circuit which is dependent to irradiation and temperature, and they can publish so many works. That is in the coming area, the coming line of year for next one in the 1 to 2 years or 2 to 3 years. This is one of the active research areas, how to model an electric equivalent circuit for IV characteristics. For example, how to model an electrical equivalent circuit for a photodiode, to be in other words. So this is the area. Maybe I'll get into the circuit easily. Yes, as I've told you, just PV is nothing but just a simple PN junction diode, where we have an anode and cathode. Is all of the stories you might know. But the interesting factor about here is, as I told you, as I've already told you, we here. I think my mouse point is visible here. I can write something here. Yeah. So if we see it here, this is going to be the characteristics of a PV. So here I can say it is 0, and this is going to be the characteristics of the red line is going to be the characteristics of a simple diode. And the next one that is very interesting to see is the bottom line characteristics. The bottom characteristics, where I have drawn it in the second I'll mark it as 2. So this is the simple characteristics of a photodiode, where when irradiation or when the incident current, when the incident current is, when the incident light is tend to fall on a PV array, the characteristics is tending to going down. The characteristics tend to push downside. It means that whenever there is a flow, whenever there is an incident solar light, whenever there is a flow of sunlight, the characteristics tend to tend to go down as much as it is, as much as it can, which means that where we can clearly see that the current level is going on pushed towards the negative direction. You know that current is always, flow of electron is always the negative line of the current. So which means that the characteristics is getting, the more and more it goes down, the more and more the current and incident solar light is higher. I repeat, the more and more the light falls, the more and more the current flow in the device is getting increased, which is simply, it says that it is a current control device. That is why we call always a PV a current control device. A very important point. We always say this as PV as current control device. Many of the researchers claim to have it as a current source. Why? Because it is totally dependent on irradiation. It is totally dependent on the incident PV current. And the characteristics is just ulta. This is minus. Just put forward in the forward direction. I can explain you clearly in the upcoming slides. So this is going to be the PV current. This is going to be the normal photodiode current. So this is going to be when irradiation falls, the current layer tends to fall in this. The nature of characteristics is pushed down, and the current in the illuminated solar cell is negative, flows against the conventional as a forward diode, as I have already told you. And the Schottky diode equation is very popular, and many of the people in the participants might be knowing it. So this is the simple idea behind how an PV, what do you call, PV cell is modeled, just by using the fundamental mathematics of photodiode. So yes, here comes a very important slide. I can explain you with respect to incident photon current. As I've already told you, forget about this RSH and RSH and RS. Forget about this. Now we have, I have already told that we have an incident solar light, and I have marked this as a current source. Why? Because PV is a current source. This IPH, this might be very clear. IPH is a current. IPH is an incident light, which is incident light is directly proportional to the current. I term this as definitely a current source. I have marked as a current source. And why the diode is given is in the sense the current is flowing inside a PN junction. So I term this as my particularly PV diode. So PN junction diode. So current is flowing inside a PN junction diode. The current direction is reverse. Why? Because the flow of current is always in the reverse direction. So there is a current source modeled with respect to my PN junction diode, and provided we need to make sure that the recombination happens in the diode proper. Number one. Number two, there should be properly a metallic contact that is to be given. So these all things has to be taken care. I repeat the concept again. I have told how a PV is modeled as a is modeled as a current source. It is IPH. The second one is going to be, it is flowing inside a PN junction. So I call it as diode. So IPH and diode are connected in parallel. And the third important factor that has to be kept in mind is the recombination that happens in the diode. The fourth important factor that has to be taken care is the metabolic drops. So the first one which is responsible is going to be IPH. Second one is going to be the diode. Third one, RS, is going to be responsible for the metallic contacts, and RSH is going to be responsible for my at the end it is going to be responsible for my recombination losses. So this is a typical electrical equivalent circuit, most popularly used in many of the literatures, many of the works. People used to electrically model this electrical equivalent circuit via, they use double diode model, they use triple diode model, they use four diode model. In different ways they extract the IV characteristics and they publish as a research article. In recent time, I have seen at least 10 to 15 papers in the last 2 to 3 months in this research area. There is a huge scope where the participants can evolve, they themselves can evolve their own electrical equivalent circuit, and they can claim that there is going to be novel, and they can compare some of the results in the literature as well. So this is one of the area where we can concentrate. And there are some equations where you can find in from literature works how the IPH is dependent. As I've told you, it is purely dependent on irradiation. We can see it here, G and G naught. G naught is nothing but the actual irradiation. G is nothing but STC. We call it a standard test condition, 1000 watt per meter square. So all these things are very normal. And TPV is nothing but standard test condition temperature, 25 degrees centigrade. TPV naught is nothing but the actual temperature. It may be 23 or 24 or 20, anything depends on the current temperature. So IPH is totally dependent on the irradiation and temperature. So the other constants can be directly taken, and we can find the unknowns and we can find the characteristics. And here comes the very important IB characteristics. As I have already told you, the characteristics of PV. So we termed as four important points in the IV characteristics. I mark one by one. This is ISC. So it's a short circuit point. At this point, you can see that voltage is zero. This point we can see, this is the second point, very important point. This is, I say it as VOC. I term this as open circuit voltage. So in this point, my current is going to be zero. So PV is highly non-linear. Why we call it as non-linear? Why? Because voltage is completely disobedient to current. It is not linear. It is not in linear relation. So why that's why we call it as non-linear. So here I have my VOC point where my current is zero, and here I have my ISC point where my voltage is zero. So at the end, power is going to be at the both the point, my power is going to be zero. Let me say one by one. Let me take this point 1, 2, 3, 4, 5, 6, and 7. I have so many points here in the IV characteristics. So when I look at this characteristics, these are the operating points like a diode where I can see using my according to my load, these points will vary. I can either operate at point 1, point 2, point 3, point 4, point 5, point 6, and point 7. And it is purely interest of the load side where it can operate. So, but my interest is always to operate at the point 5, where I call it as MPP point, where I call it this as MPP point, and this point is what I call it as VMPP, IMPP. I term this as voltage at maximum power point and current at maximum power point. So these are all very important observations before we incorporate PV with battery. We need to know what is the short circuit current of a panel, what is the open circuit voltage of a panel, what is the maximum power point of a voltage of a panel, and what is the maximum current delivered that a power panel can deliver. And the resistance at this point is what I call it as RMPP. RMPP. These are the five fundamental points that is very much required before we get it entered into a before we get it entered to integrate it for a battery. And I'll come back to this later. As I have already told you, PV is a current source. So the current, whenever the insulation falls, my ISE is steadily falling. You can clearly see this here. ISE is steadily falling. Hence, I call this as current control source. Similarly, my voltage is not having much, so more voltage is not having adverse effects. My VOC is not getting changed. When my temperature level changes, VOC changes with negligible value. So this is one of our typical observation. So the takeaway from this slide is when my irradiation changes, when my insulation changes, my ISC, short circuit current, I mean the point 1 and 2 gets changed adversely. And as you all know that we receive 230 volt power from 230 volt voltage from an electricity board, but PV cells do not have the guarantee to deliver 230 volt in a single this thing. There I need to recall my previous explanation. What is a cell, what is a module, and what is a array. I can explain it here, and I repeat the concept. PV cells are do not have the capability to deliver 230 volt to integrate it to directly integrate it to a home energy system or a battery management system. It has to be configured by the design stage, and that is where a reconfiguration stands. I can explain it clearly. I take only one single solar cell, and I take the module rating is 5 ampere, and the voltage of the cell is 0.5 volt. The total power is going to be 0.5 multiplied by zero point 0.5 is going to be 2.5 watts. So how can we generate 15 watts using a single? It is very simple. Either connected in series or connected in parallel. If we connected in series, I repeat, if I connected in series, the voltage get added up. If we connected in parallel, the current get levels get added up. But the intelligent question what we have put is we just asked 15 watts. So either you can increase the power, either you can increase the voltage rating or current rating. Either you can connect it in series or you can connect it in parallel. This is where the reconfiguration plays a major role. Either you can connect it in series or you can connect it in parallel. Let me explain you how we have connected in this particular thing. As I've already told you, higher voltage is not possible with single cell, so we are going to connect it in series and parallel. So in my case, I just prefer my solar cell to connect it to get connected in series connection. So one this contributes 2.5 watts. Now I connect all the I have connected uh, 6 cells in series, so that my this thing gets multiplied, so that I'll get it the required demand. My required demand gets satisfied. So when my cells are connected in series, my voltage gets added up. When my cells are connected in parallel, my current level gets added up. This is how we have to meet the demand. But provided we have so many calculations, we have so many problems, how to meet to the battery requirement, I'll explain one by one. So this is the requirement. Demand is 15 watts. Yes, 6 cells are connected in series. Now we have a problem with respect to solar PV, where when we have some mismatch, or when we have some kind of issues with respect to the in between cell. So how to deal with this kind of a problem? How to deal with this kind of an issue? Let us discuss one by one. This is the simpler difference. As I've told you, a cell is just a material where I have told you the some of the metallic drops RS, and I have told you the recombination of this particular PV cell. This is going to be RP, and the metallic drops is determine your series resistance, and the recombination losses of this PV this thing determines your RP. So these were the simple difference. A number of cells connected in series and parallel will determine a module, and to meet the demand from a grid side, or to meet the demand from the standalone PV system, we just connect the PV modules in series and parallel. We call it as an array. So we provide to provide 100 watts to megawatt. We use PV array in structure. And this is what I was speaking about earlier. You can this is the first time maybe you can see the figure one. ideal PV model. Very important research that happened in the year of 2000. So first model was proposed by Villalba, I remember. So it was published in IEEE transactions on power electronics. Maybe you can have a look. Ideal PV model, that was the first one without considering series and parallel resistance. The second one is with only with respect to the semiconductor and metallic drop, single diode RS model. The third one which has developed is single diode RP model. Single diode RP model is nothing but inclusion of RS and RP. And the fourth one is double diode model, where now it is extensively used for simulations and all those purpose. So maybe you can also derive your own model, not by following the same RS and RP. You can devise your own RS and RP to calculate the metallic drop and the semiconductor drop, also as well as the recombination losses. If we can do that, definitely it is going to be a research paper. It is going to, it can be, if it is well written, definitely it can be published in any one of the very good journals like IEEE or Science Direct. And this is a very important research area that is getting attention day by day, and it is getting improved day by day. And the second one is going to be reconfiguration schemes, the very major crux of the seminar. So I can explain you how this, what is the necessity of this reconfiguration. It is again a very important research area for recent time researchers. I can explain you now. As I've told you, PV modules are connected in series and parallel. I have just considered only one case. Three modules were connected in series. Let me take the case A alone. Three modules were connected in series. In the second case, and I have connected bypass diode and blocking diode. And bypass diodes is just like I'll come to this concept bit later. Bypass diode, for time being, I'll just make you to understand, like bypass diode is just like to take a, it is just like a traffic, it is just like a barricade inside the highway. If it is not the road, it is just the road is blocked, so you take some other direction. Bypass road is like a barricade where you cannot pass in a straight road. You have to slow down, you have to take the in between path. So just remember that. I'll come back to this concept later. So where these PV cells were connected in series, I assume that all in case A, all three PV modules were connected in series and receiving same irradiation. Let me say the irradiation is 1000 watt per meter square. So the characteristics will be going to be, characteristics of the PV is going to be curve 1. Maybe I can call this as PV, this curve. So the power is the characteristics is very clear, is very accurate. We can mark only one point as MPP. I repeat, there is uniform irradiation, there is no blockage, there is nothing. The current can steadily flow it. All are receiving uniform irradiation, so there is only one MPP. I call this as unique MPP. Curve 1 is very simple. So this is the first case. Second case, let me take case B. I assume that PV module 3 is receiving shade. I assume that PV module 3 is receiving shade. Assume that there is no bypass diode. There is no bypass diode, which means that PV3 is indirectly influencing PV module 2 and 1 to operate according to PV module 3 conditions. I repeat, let me say PV module 3 is receiving 500 watt per meter square, and PV module 2 and PV module 1 are receiving 1000 watt per meter square. The panel receiving lesser irradiation is influencing PV module 2 and module 2 to obey for its own current. For example, if it is receiving 5 ampere, 5 ampere is influenced into module 2 and module 1, though it can able to produce 10 amperes of current. So the current characteristics now becomes like this: when there is no bypass diode, so it happens like this. So it is something like green color direction. In this case also the power is unique. The characteristics is very clean. So characteristics is very simple. We can easily achieve MPP point. Now in the third case, let me say bypass diodes are connected. Here comes the barricade concept. In this particular characteristics, we can clearly, in this particular case, we can clearly see that one module is getting affected. One module can able to deliver only 50% of the current. For example, 500 watt per meter square. The other two can deliver 10 ampere, that is 1000 watt per meter square. These 10 ampere and 5 ampere, according to my this thing, maybe you can call it as 3 ampere and 6 ampere. It is absolutely dependent to the what do you call listeners understanding. For my understanding, I'm just keeping the shaded module can deliver 5 ampere. The other two modules can deliver 10 ampere. In this case, what will happen is there will be a reverse voltage, because since it's a semiconductor, definitely there will be a reverse voltage created by PV module 3, which will activate my bypass diode 3, which is connected in parallel. So the current direction is going to be, it is just like you go in this way. So whenever there is a bypass diode, whenever there is a dissimilar current in the string, so the PV modules will get bypassed. Very, very important concept for maximum power point extraction and array reconfiguration. I repeat, whenever there is whenever dissimilar radiation condition, I call it as dissimilar. Why? Because all modules will not receive same radiation, they'll receive various radiations. In this case, what will happen is PV module 3 will produce a reverse voltage, and that reverse voltage will activate my bypass diode 3, which in turn will be the output voltage, the current demand is going to be only for the present two modules. I can explain you with the typical case of the characteristics. Please, I request your attention here very importantly. Please listen to me. So this is 1 VMP. This is one module voltage. This is 2 module voltage, and the last one is 3 module voltage, because 3 modules are connected in series. 2 modules can deliver 10 ampere, maybe 10 or 15 or how much ever you have. I just say it as 10 ampere. 2 module, PV module 2 and 1 can deliver 10 ampere. Look, please follow here. 2 module can deliver 10 ampere. So this is going to be my maximum current value. 2 modules. This is going to be 2 module, 2 VMP. So the third module can deliver only 50%. So I just reduced. Third module can deliver 50%. If it is delivering 50% of the current, the PV module 2 and PV module 1 both can also deliver 50% of the current. So which means in this case, so all three. So when you consider, when you are making all 3 modules operate, you can able to extract only 50% of the current. When the load demands higher current, which means 10 ampere, you can only operate at 2 module voltage. You can only operate at 2 module voltage, provided you can get high current with 2 VMP. So this is the conclusion from this slide. Whenever there is a shade, there will be a reverse voltage produced by my PV module, any of the this thing, so that this particular this thing get activated. That bypass diode will get activated, and the modules which is getting this thing, what do you call, fully illuminations, they'll get they directly flow into the load, and the remaining will just stay aside from all those things. So this is also one of the very important research areas. Why I explain this much deeper is I'll explain you clearly in the next slide. So these are the various configurations, very important and very necessary for a PV researcher to know, to get the battery get configured for this PV. One is series parallel. Just connect here. The structure is 1 2 3 modules, three series connection, 1 2 3 parallel connections. So we call 3 cross 3 connection. 3 cross 3 is a structure of the PV. 3 cross 3 is a structure of series parallel. Here we have the interlinks. This is the difference between series parallel and TCT. I call it as total cross ties. Just the ties are crossed, and the last one is going to be my bridged link. So just connect the this are simple different calculations, and all the structures are 3 cross 3. Yes, here we come very important these things. So hotspot, as you know, there is any kind of problem, any kind of bird litters or something like that, there will be a problem in with respect to the PV. So there will be maybe a bird shadow, bird litter, or a tree shadow, or a pole shadow, anything maybe. So you expect a dissimilar radiation. I told you, as I have told you, you can clearly see in the slide that they experience a reverse voltage. The polarity is getting reversed. You can clearly see in the picture. This reverse voltage will activate my diode, reverse bias to forward bias condition. So in this case, it will just bypass, and it will feed to the load. So, and this is the concept what I was trying to what I was trying to say you with respect to bypass diode. Maybe in this side it is very clear, you can clearly see that this is my PV cell. The dotted diode is my sorry, the dotted diode is my bypass diode, and the current direction indicates my photodiode or my PV cell. It is just I just indicated with the current source. Why? Because it is a current control source. The dotted this thing is going to be my what do you call normal normal operating condition. When this gets forward bias is when my current illumination, when it reduces, when it is not in line with the other PV panels connected in series, then this particular diode gets forward biased, and the other conditions happen. This is very clearly known, and I have very clearly explained it, how it can be reverse biased, how it can be forward biased. Whenever there is a dissimilar irradiation, the diode will get into forward bias condition. So this is the importance of bypass diode. So yes, of course, this is the connection, typical connection, where you call it as array structure. So these diodes are nothing but blocking diodes to avoid current reversal. Whenever there is a power electronic equipments, there will be always a current reversal. So I have marked it as a blocking diode. And these days there is so many conversations and so many kind of what do you call research interest with respect to bypass diode. This is also taken once again a very good research area, how to divide the PV into segment wise, and how to derive an equation for segment wise bypass diode. Maybe this is also one of the research area where you can concentrate how this bypass diode can affect the flow of current and IV and PV characteristics. Very important research area. Maybe you can directly concentrate and take the best out of it in terms of publication. Here I have shown two bypass diode. Most often these days manufacturers provide only one bypass diode. Maybe a country wise it differs. Here in South Korea, people have three bypass diode for a cell. So it depends for country to country, but mostly in India they use one or two bypass diode for a PV module. So that is the case. And yes, this is very important and necessary, most necessary this thing for a topic, how to reconfigure PV for battery systems. So here I have a 3x3 structure. I say it as 1000 watt per meter square, 1000 watt per meter square. All, let me take case one. All 3x3 is going to be 1000 watt per meter square. So let me say my module rating is 10 ampere. Approximately I say it as one module is 10 ampere. So the row current of the first one, let me take this row alone, one particular row. The row current is going to be cumulatively, I added 30 ampere. Similarly, I add all the next step is going to be also 30 ampere. So and the last one is also 30 ampere. So all my row currents are same in the case A. 30 ampere, 30 ampere, and 30 ampere. So in the net result, I'll get very disciplined obeying characteristics of PV. That is going to be having only one MPP. The second case, what I have did is I have simulated a PV characteristics where the last row is alone 700 watt per meter square, which means here the current is 10 ampere, which means here the current is 7 ampere. So 7 plus 7 plus 7 is 21 ampere. Here I have, there is a change in current value. This is going to be 8 again 30. This is going to be again 30. So 30 ampere, 30 ampere, and 21 ampere. So in this case, there is a change in row current. Hence, there is a change in characteristics. There is a change in characteristics. I call this as first MPP. The interest is to operate always at this MPP. What I call it as global MPP, GMPP. So interest is always to operate at this particular MPP, global MPP. So in this case, the interest is always to operate at GMPP, not in the MPP2. So there is a change in row current. So there is a change in power values also. There is a change in PV characteristics as well. Now I try to reconfigure my PV. Very important. I try to reconfigure my PV by designing something, or by manually doing something, or by using some optimization, or by using some switches, or by using some power electronic sensors or something like that. Very important. Please pay attention here. So what I do is I just push my 700 to the second position, here I have pushed it, here I have pushed it. Similarly, the last row also I have pushed it to the topper portion, and the 700, the third string remains to be the same. In this case, my current is going to be 27 ampere. Here also it is going to be 27 ampere. The last place is also going to be 27 ampere. So all the row currents are same. By reconfiguring in this way, I tend to produce the same IV characteristics or a PV characteristics with only one MPP. This is very important, or this is very important research area where people used to do many kind of reconfiguration strategies. You can use a number system, or you can use a puzzle system to reconfigure this PV, or you can use an optimization system to reconfigure this PV. Anything you can use. Now I can from the case 1, case 2, and case 3, I can clearly explain you how the power is differing. For case 1, I tend to produce a maximum power of 900 watts. Similarly, I have simulated 900 watts. In case 2, there is I can able to produce only 600 watts. The maximum power I can generate is only 600 watts. Whereas in terms of case 3, just by reconfiguring PV, I can able to produce a power of 810 watts. So which means reconfiguration can certainly improve my PV power. That is what very important when it comes to battery management system or integration of PV to battery. We always tend to reconfigure PV. We always tend to operate PV at MPP, or we need to provide a characteristics which is very simple for a controller to catch MPP easily. So this is very important research area. I can say why it is very important research area. So I can say in terms of publication how it is an important research area. This is one of the papers what we have done with respect to reconfiguration. We have considered a 9x9 system where this particular all rows 6, 7, 8, 9 rows are shaded, where I can say so many dissimilarity in currents. I have the current from 8.1 to 3.6. The current range is very high. So difference between current is very high. So I used particle swarm optimization, and by using optimization method, we try to disperse the matrix, and we finally we attained with the PSO. We have reconfigured the pattern with respect to the maximum current of 6.7 to 6.4. So the current range is narrowly, is very much reduced. Maybe if you use a powerful optimization technique, you can optimize it to 6.4 or 6.5. Still there is huge scope is there. This we managed to publish in IEEE transactions on sustainable energy. So maybe this is one of the very good research areas in recent time. So we made it possible in IEEE transactions on sustainable energy. This has come out in collaboration with Denmark people. So maybe we can use. Maybe I recommend the participants to, if they are interested in reconfiguration strategy, they can use any of the optimization technique or numerical technique. By using this reconfiguration, it is definitely possible. First, you have to electrically model the PV. Then you have to simulate the characteristics and check how it is getting changed. Similarly, few other papers have come out from our collaborators that has been published in Sustainable Energy Reviews and Energy Conversion Management. So these were all like different papers where we have in the umbrella of what is that, reconfiguration strategy. So then comes, yes, now it is very easy, we have understood what is a cell, what is a module, what is an array, how to increase my power rating, how to change, what are the problems that I have with PV. I have a shade problem, I have a technique to mitigate my shade problem. All these things are clear. How to reconfigure my PV, all those things are, yes, okay, just change the connections, you reconfigure the PV, you change the characteristics of PV. That is the outcome of the learning of past 40-45 minutes that we have in the discussion. Now, how to model a battery, what are the important factors of a battery, how the battery is going to respond for my, how to design a battery management system for efficient energy storage of a PV. Of course, solar can only pump power in the to the battery in the morning time, whereas in the is well known fact. Of course, people might be knowing and wondering, but however, we need to know how efficiently we can make that power utilizable with respect to the battery, with respect to the standalone system, and with respect to the grid connected system. So the coherent idea of battery modeling starts with just Thevenin's equivalent circuit, very simple. When I just fundamental circuit theory. So we have just an EMF, or you call it as voltage source connected in series with the equivalent resistance, what I call it as RB here. So this is just a simple Thevenin's equivalent circuit. So we call it as source connected to the internal resistance for, and the voltage across these particular this thing is what I call it as battery. So this is nothing but an electrode where we have this positive and negative, and the internal resistance is going to be RB. So this is going to be Thevenin equivalent circuit. This is a simple battery model. Later in the time we started to develop battery parameters and all those things. It started to develop C naught and I naught, internal resistances and all those things got developed. And finally, we in the recent time we use battery as dynamic battery model, most commonly used. And in the recent time, so many battery models are there, but still some of the prevalent battery models that is available in literature is the third diagram, dynamic battery model. But the fundamental has started from only Thevenin's equivalent circuit. I have given what is CCB is nothing but the battery capacitance, RP is nothing but self-discharge resistance, RIC and RID is nothing but internal resistance during electrode and battery plates, ROC and RD is nothing but voltage drop resistance during charging and discharging, and C0 is going to be double layer capacitance. And irrespective of this equivalent circuit, there are four important parameters to learn in batteries. Are nothing but one is SOC, state of charge or strength of charge. Second one is depth of discharge, DOD, and battery voltage, what is the rating of the battery, and the last one is ampere hours. I'll explain one by one. I have not given it in the slide, but still I can explain. State of charge and depth of discharge is indirectly proportional. For example, in the mobile, we have 100% battery, which means the strength of charge is 100%. If the battery reduced to 80%, we call it as the state of charge is going to be 80%. The opposite is going to be the depth of discharge, how much it has discharged. 20% or 30% or 40% is going to be the depth of discharge. So that both of them are opposite terms, very crucial terms that demands more attention. The last one is battery voltage. It may be rated for 12 volt or 13 volt or 14 volt or 15 volt. It depends. But mostly we have it as only 12 volt. And the last one is ampere hours. Ampere hours is nothing but how much amount of constant ampere it can deliver within an hour. It can be clearly explained. It can be clearly seen in the next slide, in the battery characteristics. Yes. So this is the battery retention ratio. This is the storage period. The more the temperature is less, the efficiency or the retention ratio is high. For example, if we have even it happens with the mobile phone also. The same mobile phone I used when I was in my home country, the depth of discharge was very faster because of the temperature conditions. When I came back to the some other different to different country, the depth of discharge is different. So it purely depends on the temperature. So when the more the temperature is lesser, which means the capacity retention of the charge capacity of the battery will store for a long time. Maybe you call it as an operating temperature. It also depends. This is the first conclusion from the capacity retention characteristics. I repeat, the more the operating temperature or the maintenance temperature is lesser, the more the retention will be high. The more the retention will be, the more the efficiency will be. So that is what it says. And with respect to terminal voltage, it is very important. The more the terminal voltage, which means the capacity of the battery is high. For example, if it is a 12 volt battery, if it is fully charged, it should read 13.1 or 13.2, which means the battery is fully charged. If the battery reads 12.0, which means the battery is getting drained or the battery is already drained. That's what the characteristics clearly shows. The more for example, let me take this as 12 volt battery. This is a characteristics of a 12 volt battery. This is approximately 11.5 or something like that. The charge in this is very less. Similarly, or the drainage period is very less. Let me take the point number 2. the highest point, the charge available in the battery is very high. The characteristics typically shows that the more the voltage measured during the open circuit time determines the battery, what do you call, characteristics of, determines a battery operating level, or determines a battery healthy period, or during that particular charge state of a battery, to be particularly speaking. So this is what it is. And how to integrate battery with respect to a PV, I'll explain it in the next, in the next, for the next 10-15 minutes. So here comes the role of power electronics. So we have typically, so I'll just finish this slide, then I'll come back to this slide. So we have a PV array. Let me say this as a 12 volt battery. Let me say this as a 12 volt DC battery. Let me say this. Let me say this as 24 volt PV system I have connected. So I have a DC converter where my PV can push the power via converter to the load. Of course, it is possible. And whenever my PV is in the on state, it can also deliver my power to the battery, and battery will get charged. Whenever my PV is not there, my what is my battery can supply to my load. This is the operating mode. I repeat, PV delivers two operating modes. One, it can directly feed power to the load, or it can able to feed power to the load as well as it can charge the battery. And when the load is insufficient, or when my PV power is insufficient, both can do the purpose. Both can solve the purpose. This is mode A. Mode B is nothing but only PV alone delivers to the load, as well as PV delivers to the battery charging. This is mode 2. Mode 3 is during the night time, maybe evening time, where my battery alone supplies to the load. And the last one is both got drained. Nothing can be done. I mean, there is both is particularly gone for an outage, where both is not been operating. Both of them are not in an operating stage. So these are the various operating modes. In recent times, we have so many research articles based on this operating modes of a PV, how to manage the DC link voltage, or how to manage a common voltage with respect to PV and this thing. This is very common. Maybe I can show it to you with respect to battery energy storage systems in a clear picture, in a better picture. Yes, it is very clear. I can show you. It is, my PV is going to be 150 to 300 volt. I'll say how to make this 150 to 300 volt in the last slide. How to make the PV 24 volt PV to make it into 150 to 300 with some safety measures, or with respect to some ratios. I'll explain you in the last portion of the slide. So I have just made my PV array to convert 150 to 300 volt. This is nothing but my simple converter, where my voltage is delivered to my load RL. So it is just a unidirectional DC converter. In this particular converter, I just have 150 to 300 volt, where it is feeder to 100 volt DC, which is a buck operation, again a buck converter. So this particular line is 100 volt in the top section. So I always try to maintain 100 volt. So this is very important in terms of DC link. This is DC link capacitor, where you have it is always maintained with 100 volt. So both the sides, it is the duty of the output capacitor to maintain some voltage. So which is like always mandatory to have a common voltage. So always it is required to have a common voltage. So the output is going to be 100 volt, and this output is going to be 100 volt. So always it is required to maintain 100 volt. And the battery side, we have used buck boost converter, or you can use converter, or you can use any kind of a power electronic converter. So but it has to do the both operations, buck operation or a boost operation. When it is doing buck operation, which means that my battery is charging. When it uses the boost operation, which means that my battery is feeding power to my load. I repeat, when it uses buck operation, which means that my battery is charging. When it gives boost operation, which means it is delivering to my load. So that is, these all things can be controlled by a single microcontroller, just by giving pulse to this converter, this pulses. This is yet again a different research area. How to control pulses for what do you call energy management system. This is what we call it as PV with energy storage system. How effectively, how efficiently you can able to control the power or a power flow for a standalone system or a grid control system. I repeat the concept again. My PV has 150 to 300 volt, and the purpose of my DC voltage is to have my 100 volt DC. I commonly I connectedly I store it is a responsibility of the output capacitor C2 and CH2 to maintain 100 volt DC all the time so that my load gets satisfied. These are the first 2 points. So here I use a buck converter in the unit from PV to load. So where it reduces my generated voltage from PV to constantly 100 volt DC. And if PV is good enough to deliver power to my battery, this particular bidirectional converter will operate in buck mode and store the charges in battery. If my in case if my PV power is absent, my battery tends to operate in a boost. My battery tends to feed power to my load by making my bidirectional DC converter in boost mode. Maybe a common question can raise: who decides like to operate in buck converter or boost converter or a buck boost converter? These all things were decided only by an efficient energy management system, and that all depends on the wisdom and knowledge of the controller what you are designing. And it's a very important research area. It is still been actively being researched by Deakin University, Denmark University. Many people are doing works on this active feed forward loop, current control system, open loop system. Many things are happening in this research area. Still an active research area. Importantly, you can deeply look into it, and you can take a call on power electronics as well. So energy management system for PV battery storage. So this is how it works, and this I have told you how an operating mode and all those things happen. This is yet again I have told you a different system, maybe a boost system connected to a PV device, and unidirectional power control. I have taken the reference of IPV, VPV, and VDC, and battery control. I have taken the switches. I just provide these. This is the controller. This is the energy management system controller, where these are my inputs: IPV, VPV, VDC, and these are all my input. This is my common DC link voltage, where I have to maintain some common voltage. It depends on the load or voltage converter. If it is single phase, you have to maintain 300 volt. If it is a three phase, you have to maintain 600 volt. These are all common stories that all people might be knowing about it. So there is no need for separate explanation for this. But this is yet again a very important topic for research, unidirectional and bidirectional things. So you can actively look for this research particularly. I have given some straightforward these things. So you can maybe if I share the slide, you'll be able to see the contents in it. Yes, I have come to the conclusion of the session. I have already promised you that how to design a PV system for a simple house, or how to design a PV system for a day-to-day life, for a small nano grid or a micro grid system, how to design my PV. So I have just choose some of the sample sample what do you call wattage or something. I have chosen 4 CFL, which is running for 8 hours, 30 watts each. I have chosen DC fans, 2 DC fans, which is running for 10 hours, 45 watts. I have chosen one TV, which is 200 watts, which is 4 hours. And I have taken refrigerator 500 watts, which is running which is able to run for 16 hours. So totally, when I calculated ampere hours, means I need to design my battery, I need to design my PV system. So the total I need to approximately know how much amount of watt hours I require for my nano grid system or a micro grid system. So what I do is I just multiply it, and I get for CFL cumulative 960 watt hours. Similarly, I have done it for all the systems, and I've come to a conclusion total watt hours is 10,660. So total watts of this particular thing is 775 watts, whereas the watt hours, how much amount of hours in operation, when I calculate, I have come to a conclusion like it is 10,660 watts. And as we have already known that what is a watt hour and all those things, so I have just, for safety side, for reader understanding, for participant understanding, I have just given 775 watts and 10,000 watt hours are the total this thing. The first and foremost thing is to determine what is an amount of current it is required. So it is very straightforward. We use nominal of 24 volt as PV cell as voltage. So I just take it as 24. So that watts divided by this thing is going to be 5.6 ampere. So my system should always deliver 5.6 ampere so that it can able to feed my system. That is the point number one. Next is to determine ampere hours. Very simple. Just total watt hours divided by system nominal voltage. I come to a conclusion like 446, 444.6 is my watt hours estimation of ampere hours. The next step is to going to determine my battery sizing. Battery sizing is also, it is very simple. Um, for any PV array, for any this thing, we need to know what is effective sun hour. So for example, if in a day I have 6 hours, it may be 7 hours depending to the season. So I just estimated total number of ampere hours is by estimated ampere hours by estimated sun hours divided by days of autonomy. For example, it is having zero 0.6 as days of autonomy, and estimated sun hours I just took only 2 hours. It may be 6 hour or 8 hour. It depends according to your own system or your own climatical condition. So I have taken estimated sun hours as 2, days of autonomy as 0.6. These two are very important terms in terms of battery calculation. So whenever you determine the how to know what is the ampere hours needed, you need two factors. One is days of autonomy and effective sun hours. Effective sun hours is nothing but in relation with irradiation, how long you can able to get the good irradiation. I just determine it as 2 hours. It may be 6 hours or 7 hours in a day, it depends. So I just took based on calculation, I came to know we came to know that 1480.5 is the ampere hours it is required. By considering safety factor, always 90% efficiency, it may be 80% also efficiency, it depends. I always treat it as 90% efficiency my system. So on conclusion, divided by 0.9, I'll get 1645 as my total ampere hours. So we came to know one, the battery system what we are going to design should be able to should deliver 1645 ampere hours capacity. So that is a total design, and based on the calculation, let me take it as 12 volt battery. It depends, you can take 24 volt battery also. It clearly says that you need two batteries in series. So 24 divided by 12, because we have considered only 12 volt battery. If it's a 24 volt, yes, you can go for directly 24 volt, and that is with respect to voltage demand. With respect to parallel demand, we need 50. Why? Because it is of, I have just considering what do you call 50 ampere hours battery capacity. In that case, 1645 divided by 50 will give the total amount of batteries connected in parallel. So my configuration is going to be 2 cross 11. That is my PV battery sizing to meet the required demand, to meet the required power load. Where in terms of PV, it is very simple. I have taken a PV with 55 watts, VMPPS 17.4, IMPPS 3.3. The structure is very similar. So 24 by 7.4, you get 2. And with respect to number of batteries connected, it is also 2. So the structure is going to be 2 cross 2 for battery, and 2 cross 11, sorry, 2 cross 2 for PV, and 2 cross 11 for battery. So this is how we can simply design a microgrid or low voltage DC grid system for a PV or a efficient energy storage system. Always keep in mind that you need to have a depth of, sorry, state of charge, depth of discharge, days of autonomy, effective sun hours. These all factors are very important before you design a PV sizing or before you design a battery sizing. These are all the important factors before with term this as what do you call effective nanogrid or a microgrid system or something like that. So after this, maybe you can able to you will be able to design. Once this is designed, you can able to design the converter, and you can go for independently a separate PV system or a PV manufacturing system or something like that. It is very useful. These data were taken from our own publications, our own research, from different kind of environments, different environmental conditions. So these were our universal collaborators of POSTEC in our particular lab. So we do collaborate with many people. So these were the contents we have developed in the last 4 or 5 years. Various people we worked in. We have worked with Sofia University, Japan, Denmark, Aalborg University, or University of Roma, Italy, Statsland University, United Kingdom, Petrona University, South Africa, and University of Technology, Malaysia, UTM. So some of the countries are missing, but still these were the major collaborators for us in post-tech. So I just conclude by opening the forum to audience, and I also sincerely thank my beloved HOD sir, Dr. Kumar Chinayan sir, and my beloved faculty, my guru, Dr. Uttarasamy sir, and Karpagam ma'am, for being a mentor, for being the uh, playing a huge role in my career. I am the student who have come to a different stage. So I just thank all three of them who have been a strong pillar of support and who gave me an opportunity to speak in front of the audience of KPR. Thank you so much, and I leave the forum for the queries. If you have any queries, I'll be happy to answer.
Participants, if you have any queries, kindly interact with the resource person. Participants, if you have any queries, so kindly interact.
We can, sir. I have got some questions, sir. There is a question from Sundaram Marudachalam. Sorry, I would have missed Mr. or Doctor. Please don't mind it. We may use static switch. There is also a publication in static switch, and there is also dynamic switches also we can use. We can use a power electronic switch also. It depends on the preferences. Probably if you use power electronic switch, and if you are able to reconfigure, it will become an IEEE transaction. You can definitely go for it. I hope I have answered this question. The second question is, what is loss, mismatch loss? Mismatch loss is like when a PV is operating in normal operating condition, you get a power of 810 watts. When a PV is operating in shade condition, I just say it as you produce 600 watts. But when you reconfigure it, you have a power of 810 watts. Sorry, you have a power of 710 watts. The reduction in power and improvement in power is what you call it as mismatch loss between the shade case and the non-shade case. That is what probably I can share you the formula to calculate mismatch loss. Megawatt, what about the cost? If yes, what about the cost? It depends, sir. It depends on the type of what do you call wattage rating, or depends on the type of unit rating what you give it for a country to country. So it entirely depends. Thank you for giving very good feedback. Any ways to improve efficiency of the converter and panel? Of course, there are so many ways to improve the efficiency of the converter. We can definitely improve the efficiency of the converter by using silicon carbide devices, and we use so many kind of what do you call efficiency improvement with respect to power electronic devices. We typically speak about on-state resistant drop of a MOSFET and all those things. So when it comes more about efficiency improvement of a converter, we need to speak more about it becomes a different session with respect to on-state resistant and off-state losses, switching losses kind of stuff. And it more deals with respect to gallium arsenide or the type of semiconductor we use in the system. So this is what it happens with respect to improving the efficiency of control. Panel, there is no choice. It is still 17% or 18%. If you can able to improve to 21% or 21%, I swear you people will be going to be a billionaire. So this is going to be the deal of the day. So if you can improve by using some technology to 22% or 23%, definitely you will be a billionaire, and you will be most wanted person across the globe. So by using some technique, by using some kind of a semiconductor material, if you can do it, that is going to be a deal.
Participants, any more queries? So I hope there is no further queries. So saying thank you is more than a good manners. It is a good spirituality. In this cheerful occasion, with an immense pleasure, I take this opportunity to propose the vote of thanks on behalf of management, Department of Triple and organizing team. I feel honored and happy to thank our today's resource person, Dr. J. Prasadram, who has shared his wide research experience related to the configuration of PV system, charge controllers, unidirectional and bidirectional charge controllers for a PV system, charge storage system with a buck and boost converter, and power flow control with a buck boost converter, how to design an energy management system for a home appliances. So thank you so much for sharing your wide experience, Professor. So thank you so much. Happy
Thank you.
learning. Thank you.
Sir, hello, hello.
Yeah. Audible.
Sir, can we listen from any one of the audience for the feedback?
Sure. Participants have any feedback regarding this session, please? Anyone, please.
Okay, sir, then it is not a problem. Then
Yeah. We will
I'll
share the consulted feedback today evening, Professor.
okay, sir. Thank you.
Okay,
Thank you,
thank
sir.
you.
Thank you.
Thank you
Bye, sir.
once again. So